Shall we start or we can wait a few minutes, like a couple of more minutes for the attendees to
They
join?
will join. They will join.
Okay. So
तुम्हें लाए नहीं हूँ आज मैंने घर पे ट्राई किया इसको चलाएं
Shall we start?
okay, so I think
नहीं
we have a few attendees right now.
स्पीकर आवाज चलती है ना
So shall we begin?
Please start.
So a very good afternoon to all of you present here. My name is Sharad and I have the privilege of being here for today's event.
अभी दो बजे होने के बैठ जाते हैं तो बताएं मुझे
am I audible?
आवाज नहीं आ रही
Yes.
You are
Sharad,
audible.
I cannot hear you. Can everybody hear Sharad?
Yes.
Okay, great.
We can hear.
So thanks a lot for joining us today. Just as graphene revolutionized the world of material science,
हमेशा चलता है
quickly emerged as a captivating protagonist in the ever-expanding universe of two-dimensional materials.
इससे फर्क पड़ता
From the chemical element boron, graphene exhibits remarkable properties that set any material that came before it.
है you go to real tech
With extraordinary strength, flexibility, and conductivity, graphene has the potential to surpass graphene in many key aspects. And today, I feel honored and privileged to share the screen with the esteemed speakers, guests, and all of the attendees. Once again, I extend my warmest welcome to all of you. I'm confident that the knowledge shared during this event and the connection forged and the ideas sparked during the tenure of the event will propel us into the future where graphene reigns supremacy, revolutionize industries, and transform the world as we know it. So, welcome all. Now, I would request Shri Raju Goyalji, Secretary General ELCINA, for the opening starts. Goyalji, the screen is yours.
Good afternoon, Sharad. Thank you for our introduction and this introduction and for starting off this first tech talk. So my name is Raju Goyal. I am from Electronic Industries Association of India, and at the outset, I would like to thank Mr. Amrit Manwani, sir. Thank you for joining us on behalf of ELCINA and sharing some of your thoughts about materials for electronics. Mr. Manwani is also a past president of ELCINA and the chairman and managing director of Sahasra Group. I would also like, I would like to especially welcome the three young, professors from IIT. From all three of you are from the metallurgy department, I see, and I think it's great to have you here, and we really appreciate this particular session. I would just like to say a few words about what ELCINA is doing in this area. So this initiative is actually part of the ELCINA Workforce Development Group, which is also part of our semiconductor and electronics group. And this is been formed along with ESSCI, the Electronic Sector Skill Council of India. Our main objective here is to try and bring experts onto these tech talks, and this is also educative, not only for students but also for technology experts from the industry or those who are from the engineering side, the science side, and I think this is one initiative that will add a lot of value. We are especially looking for this to add more value in the realm of semiconductors, where a lot of work is happening right now, and I think new materials have a lot of role there to play. So I would not like to say anything else, only that we are looking forward to more such tech talks, and in fact we've already planned the next one on advanced packaging in semiconductors. That's going to be after a month approximately, and we'll announce these dates. Other than that, I don't know so much about Borophene, except that I believe it is going to change a lot in the electronics world, and I think it has some properties which have great potential for for mankind and for the products that we make. And so, with those few words, I would like to leave the mic now and request Mr. Manwani to kindly give his special remarks. on behalf of ELCINA and ESSCI. Mr. Manwani is also the chairman of ESSCI. And then it will be over to the three young professors to take this forward. Over to you, Mr. Manwani.
Thank you, Raju, and good afternoon to all of you. It's a pleasure to be on this forum. This will give me an opportunity to hear out what are the new advancements that are taking place in materials in general and electromaterials in particular. As Mr. Raju Goyal said, I also don't have much knowledge of Borophene, but all that I've heard is that it has very high tensile strength, matching with carbine, I think. And my knowledge of Borophene stops there. But the fact remains that many years ago, in electronics, one only focused on the electronic side of semiconductors or electronic products. However, over time, the importance of electronic material or materials in general has become paramount. When the first transistor was invented, we only learned of silicon or germanium transistors. But as time has progressed, we've seen what materials, what kind of role that they have played in electronics. And, most of us now, those who are involved with electronics in some way or the other, recognize the importance of all kinds of materials, whether it is in a manufacturing process or whether it is in making of components or products, etc. In semiconductors particularly, silicon continues to play a very major role. It is the basis of most of the semiconductors that are made, particularly in memory space and processor space, controller space. However, as we have progressed, we have recognized the need for other materials to be used more effectively, like silicon carbide, etc. But there are other materials which go to make a semiconductor. For example, when we are looking at packaging a wafer into an active semiconductor, we are looking at resins, we are looking at substrates, which are made of ceramics or fire retardant materials. Then, thereafter, we have to get that wafer connected to the external world, and therefore we used all kinds of wires, whether they may be gold or silver or copper or aluminum. So all these materials become very, very important. The dimensions, the electrical characteristics, the conductivity characteristics become very, very important. I'm glad to note that we have experts today talking about Borophene. Whatever little I've heard of Borophene, it will find significant application in energy storage devices, batteries or whatever. Traditionally we have known only lithium-ion batteries, but with other materials coming in, it's really exciting world to know about electronic materials. I'm sure as we go along, the mankind or the engineers, the young engineers of the current generation will find out newer materials which will only improve the productivity and application of semiconductors and other electronic devices. So with that, I would like to wish all of you a very good afternoon, and I would definitely look forward to hearing all of you. I come from a older generation where we had very limited knowledge about electronics and certainly semiconductors. But so much of advancement has taken place, and with semiconductor industry growing by leaps and bounds, whatever the development that took place in semiconductors in the last 70 years is going to double in the next 7 years. So evidently, there will be a lot of excitement in this space, and we look forward to hearing from the experts on Borophene and other electronic materials. Thank you very much. Over to you, Raju, back to you. Maybe you are conducting or moderating the session. So over to you.
No, thank you very much, sir. Thank you so much. And Mr. Manwani is also, an alumni of IIT Kanpur. And sir, we know that those who have had the original ghee have got, much stronger, constitutions than, than the younger generation, which is not getting that, that pure stuff anymore. So I think, and also Mr. Manwani is the first one to have, started a project in semiconductor packaging in the country, which is a very bold initiative. And I think it's going to, encourage others to join and make ours a strong industry. So, sir, I don't really have anything else to say except now, leave the floor to the experts. So, Saurav, over to you. You can please kindly take over. You are there, and Mr. Dubey is also there from ELCINA. And we look forward to hearing now, and we won't do any more talking. So, over to you, please. Over to the experts. Thank you.
Thank you, Mr. Raju Goel, Mr. Amit Manwani, Saurav, Mr. Dubey, everyone. Thanks for joining, and thanks all the audience joining from outside the ELCINA. So myself, Dr. Pranay, and my other colleagues, Dr. Devanshin Negi and Dr. Amitav Banerjee, would like to present a presentation on Borophene. So allow me to share my slides. Is it visible?
Oh, yes, sir. The slides are.
Yes, yes.
So today, in the next few minutes, we are going to discuss about Borophene, which is being considered as a new wonder material, and that's a new sensation in this 2D flatland. And of course, it's been deemed to go beyond graphene. So first of all, we'll see the content of the talk, where we'll talk about Borophene. In that, we are going to talk about the impact of Borophene on technology. What is Borophene? What are its polymorphs? And I'll brief the synthesis technique, how it can be made in the lab or at the industrial scale. Then we are going to talk about why Borophene is required and how this problem is of global importance. Then few certain interesting results will be shared, where optimization of the synthesis process based on few key physical input will be discussed by Dr. Devanshin Negi, and then computational aspect will be dealt by Dr. Amitav Banerjee, where he is going to discuss the insight of the synthesis condition, and he will also try to understand or to explain the potential of Borophene in different applications. At last, Dr. Amitav Banerjee would be ending up with the potential of Borophene in the world market. So to begin with, we have tried to summarize the concept of Borophene based on the market of the current market. So we found that Borophene world market is near about $106 billion US. That's being reported by Gajetsu, and in between 5.7 billion US dollar has already been industries has already been there in the market, which are making optoelectronic devices from Borophene. In the energy sector, it's been predicted that 30 billion USD would be the infuse of the money in the energy sector. So these are few crucial numbers which we want to talk about. But before that, it is important to understand that we are the pioneers in the research of Borophene, as we are the first to present the synthesis of Borophene, freestanding Borophene, to the scientific society through sonochemical, chemical, and micrometal exfoliation. We overcome this hypothesis that it cannot exist in a freestanding form. Recent articles from Tesla and different companies suggest that, even MIT reviews, it suggests that it is going to be the next graphene. But how? That is, we are going to talk in next few minutes. We are also going to discuss few phases of Borophene, which is quite relevant for its electronic purpose. And we are more inclined towards the beta 1 and the chi3 phase, which are the 2D phase of Borophene. We are also going to discuss few applications depending upon the optoelectronic sensing, energy storage, and generation. Dr. Banerjee will be focusing his talk on the structural and electronic phase of Borophene, because that will govern the application part. So he will be basically investigating the inside of the electronic properties, and Dr. Negi will be telling how this atomic structure would define the end properties. So based on all these assumptions, we together came up with for the presentation, because I have the expertise of synthesis. Dr. Banerjee has an expertise of the atomic arrangement and atomic understanding of the atoms. And Dr. Banerjee would be talking more into the computational aspect, because he can tell us how the atom will lead to change in the application format. So before that, we need to understand what is Borophene. So Borophene is basically a monolayer sheet of boron. It's a new class of material, unlike graphene, which is semi-metal. MOS2 or transition metal, those are semiconductor, and boronite, which are insulator. Borophene is semi-metallic, which is a new class of material. So it's the lightest anisotropic material, which is metallic in nature. However, its structure is quite complex, because it's a 2 and 3 center boron to boron bonds. It's the most complicated structure till date in the history. So it comes from a family known as zenes. So zenes are basically group 3, 4, 5, 6 elements, where Borophene comes from group 3, and it is the mono elemental material. However, if we consider why Borophene is required, then we should understand in very short the properties of Borophene in respect to other 2D materials. So in this figure, I've tried to summarize different 2D materials based on metallic, semiconductor, and insulator. And on the y-axis, I've tried to summarize the band gap and the mobility. So in case of Borophene, that is represented by B, you can easily see that the mobility is more than graphene. However, if I'll go for the Young modulus, again, it's more than graphene or compared to any other 2D material. So now we have two advantages, which is the Young's modulus and the mobility, which is more due to the anisotropy in Borophene, and no 2D metal in parallel exists to Borophene. However, if we consider graphene as the base or as the first 2D material, which has kept the foundation state of 2D material in the real world application, graphene do suffer with different kind of lacunas, where the first can be dealt as lack of electronic band gap, because it's a semi-metal. So semi-metal don't have electronic band gap, but we in the scientific community, a lot of assumptions have been made and a lot of experiments have been done to induce doping to open the band gap. However, due to doping, the mobility used to get decreased. At the same time, if you see, transition metal dichromates has been widely been explored, but they lack in thermal stability and poor mobility. Now, at the present time, only two anisotropic material, that is the phosphorine and Borophene, has been investigated with great scientific interest. However, phosphorine is not always famous for its flammability property. Therefore, we left with the option of Borophene. But the problem of Borophene is that it's a non-van der Waals material, and it has an icosohedron structure. So till 2019, there was a hypothesis in the scientific society that since it's a non-van der Waals and has an icosohedron structure, it cannot exist. It cannot be exist in a freestanding film. However, few seminal results from Mark Hersamgren from the Northwestern and Wu et al. From the Chinese Academy of Science, they published that Borophene can be deposited on a substrate. And they did this calculation and hypothesized that it's a substrate mediated growth. That means the atoms of the substrate is governing the growth of the Borophene. Again, they said that it cannot be met in the free existing sheet. However, if there is a substrate, that will limit always the application of the material. So we need to overcome this kind of hypothesis where there is a substrate. At a similar line, Tai et al. Tried to deposit Borophene through CVD. However, this group failed because that is a very thick layer of boron and it cannot be called as a Borophene. So after all this hypothesis, I came up with my technique where I have tried to exfoliate Borophene through sonochemical exfoliation. So I tried to optimize the solvent energy and the material phases, and then tried to exfoliate through different sonochemical time as well as frequency. So indeed, all this characterization technique has been done, different characterization technique, including Raman and XPS, just to confirm that the material has been met in the right phase and purity. However, when I was trying to investigate the properties of Borophene, I ended up with having two different kind of structure, that is the beta 1,2 and the chi3. What was phenomenal here is that we found a new phase, that is strain mediated phase, and that do exist between the beta 1,2 and the chi3 phase. So we try to dig up more into latter part of our research, because at that time we don't have a very good TM. However, we tried to end up with the different kind of application, and we found the metal to be phenomenal, because even at the room temperature, there is a density of state clearly been shown in the image C, where we got the quantum state at the room temperature. In B, you can see that even at room temperature, it's metallic in nature. That's a very different kind of material which we are talking about. That is a metallic at metallic 2D material, which is a new class of material. Even we tried with different kind of SES platforms. So what we found that even Borophene itself gives us a SES platform. So this make us think about why cannot this metal be synthesized at large scale. So just like an analogy of graphene to graphene oxide, we tried to make Borophene oxide through chemical route, and we ended up with a pure phase of Borophene oxide, and the scalability has been changed from milligram to gram scale. So this report was published in Advanced Material. Later on, I tried to exploit the same Borophene through a new technique known as micromechanical exfoliation, and I ended up with the Borophene sheet. Again, the hypothesis got broke that you cannot exfoliate Borophene through micromechanical exfoliation. Looking into more detail, we again ending up with the beta 1,2 and the chi3 phase, which are the two 2D phase of Borophene. And when we did this different spectroscopic investigation, we ended up with the fact that the phases has been met in the right phase and purity. This was again published in Advanced Material. Later on, we tried to summarize all the synthesis technique in the market, and what we found that out of the 5 techniques, 3 of the technique has been given by us. Okay, and we are the only one in the world which present this freestanding Borophene, and we started the application of Borophene. Otherwise, with the other techniques, only the intrinsic properties of Borophene are in talk. You cannot implement in the real life examples. Then we summarize the band gap and mobility, which we talked earlier, as well as the thermal conductivity, where we found that Borophene has a very bad thermal conductivity. It's not as good as other 2D metal. However, it's comparable to boron nitride at some stage, or phosphorine. Then Young's modulus, we found that this material is the best among all class of 2D materials, and we tried to find out different application of Borophene in different areas like photosensing, energy conversion, SES, strain sensing, energy storage, and gas sensing. And we tried to summarize all the challenges which 2D material do get before ending up with the device. So these are basically at the lab scale we tried to summarize and publish. Now we came up to the industrial scale. So we tried to summarize the supercapacitor behavior of Borophene, which is basically in talk, and why it is in talk that Dr. Amitabh Banerjee is going to talk, why Tesla is behind all these things. So we found that all the sulfides, whatever present in the literature, they have maximum have a 800 to 900 farad per gram specific capacitance. While when you talk about metal oxide, we found that it's again goes to a bit high, like 1200 or 1400, but we have to remember that it's of ruthenium oxide, which is a very rare transition metal. Now in case of Borophene, we found that the result has been phenomenally dramatically increased by 3-fold. We went up to 1800 farad per gram. So this was something new which we found in Borophene, and that can be hugely like get impacted in the real-time application. In addition, with the help of IIT Jodhpur, which is a private firm at Jodhpur, we tried to make different kind of radar absorbing materials. So let me clarify this, that this is the world first kind of coating what we are going to develop with IIT Jodhpur, where Dr. Satish and Mr. Ankur is with us from the IIT side. And we try to make a radar absorbing material which can absorb the radar even at high temperature. So till 500 degrees Celsius, we have absorbed 90% of the radar, which can be applied to the rear part of the engine of the fighter jets. So presently, if you see in the recent literature, especially India lacks in this kind of technology. Even in the world, is no such technology exists where you can coat on engine, and due to the thermal signature, you can obviate the fighter jet's signature. Suppose you have Su-30 or MiG or Rafale. So they all have a different engine, and these engine have a different thermal signature. Now, this thermal signature can, like in the reverse engineering, can tell you what kind of fighter jets is in the domain. So we are trying to develop a coating which can absorb rear radar cross section adsorption even at high temperature. So till 500 degrees Celsius, we have demonstrated and got certified from defense lab, and we are trying to develop till 900. But at 900 degrees Celsius, which is the ending point of the fighter jets high temperature, we found that our material is changing the color. So we are in at present we are working on this. However, still at 900 degrees Celsius, our material is in good shape. It does not lose the additional strength, but the changing color is a concern for us, and we are working on it. So this is basically been process or the process in development, because we are trying to finalize the composition, and we are very sure within a month or two we will be coming up with a solution where this can be applied in a real-time fighter jets engine, and even the it can absorb at high temperature. So this kind of coating is not existing in anywhere in the world. However, we are almost very close to develop this kind of technology. Now I'll request Dr. Negi to go ahead from here. Dr. Negi.
Yeah, thank you, Dr. Pranay. Am I audible? Hello.
Yes, you're audible.
Yeah. Okay. So thank you, Dr. Pranay, and thank you all esteemed member of ELCINA giving us this opportunity to present our work today. So I mean, this team basically provide understanding of atomic scale of this material, and that help us to give this information to the Dr. Pranay, who's synthesizing, or either Dr. Amitav Banerjee, that who can just model and do some sort of calculation. So it goes back and forth to enhance our understanding. So before this, Dr. Pranay has vividly, highlighted how this material is very important and can even has a promising potential to replace the graphene, and it is finding application for electronics, for defense, and from energy storage, and many more. So, but we have to understand that we are talking about a material which is one atomic layer thin. So in order to understand it, to basically, to gain more and more understanding, so we can control and engineer this material, we need to have, atomic scale understanding. So in this context, there is a requirement of transmission electron microscope is inevitable. And it's very general, because if you see around us, everywhere we are using materials, and these material has certain functionality at atomic scale, which invariably gives its property that is used for any electronic devices, right? So, and human civilization is in fact built on the development of these all materials. Let's say from Iron Age to bronze, silicon, and probably in the future we could go to, quantum material. But these materials are ubiquitous, and they are used in different form, which are running our daily life. But if you just slice it down at the end, you'll find that the atomic structure plays a crucial role to govern the properties of these materials. And in fact, in the science community, there was a famous saying of Richard Feynman, who says that there is a plenty of room at the bottom, which means that if we understand the material at atomic scale, we can understand uh, how it behaves, and then we can basically engineer the material, right? So therefore, understanding at the atomic scale is very crucial, and therefore we required some sort of instrument. Next slide, Dr. Pranay. Yeah. So, so to see the material at one atomic scale, we can use a different instrument. But if you see this slide, the TM basically surpasses the resolution limit. The modern aberration correct electron microscope gives you the capability that even you can see a single atom. So in the last image, I'm basically showing there is a one heteroatom is just above the graphene, and these modern transmission electron microscopy gives the capability to even, to see these atoms individually, and not to see in fact, but to quantitatively characterize, right? So next slide, Dr. Pranay. Yeah, so as I said, that I joined this team to provide this atomic scale understanding, so that we can understand this atomic scale material. and I've been trained as an electron microscopy. And in fact, I was using India's one of the first double aberration corrected microscope in JNCSR Bangalore. And I was also operating these aberration corrected microscope in Max Planck Institute in solid state research in Stuttgart, Germany, where I was using various techniques to understand the material at atomic scale. Next. Yeah. So coming to the Borophene, we have different key challenges while we are going to understand this material. For example, we first to understand the structure of this material. This material has 16 allotrope, and recently there was Rice University, there was a report that this material could have 100 and plus phases, and probably some phases has some specific property. Therefore, it's a very crucial to understand all these phases and therefore understand the structure, right? Now, at this atomic scale, there are these atomic defects are very inevitable, and these defects also plays a crucial role to give some sort of property these material. Right? Dr. Amitav will also highlight during this calculation part. But to understand it, we need to see, and these modern microscope gives you the capability to, examine these kind of defects and just to find that how these defects are impacting the property of a material. So therefore, it's a very important. Now, dislocations are there also. These kind of defects also impact its property. Now, this material, there was like previously there was a hypothesis that this material can only be grown on some specific substrate. For example, it's a gold or silver, but our team has break this myth and have first Dr. Pranay have first time shown that this can be grown as a freestanding, and that gives the opportunity for upscaling this 2D material. So it's a very important to understand that how this material grows, so that we can reinforce our understanding, and that will ultimately give us a knowledge that how we can upscale the production of this material. So these all understanding can be gained through this microscopy study. And then electronic phases. Yes, electronic phases are very crucial to understand because they link up its functional properties. And as I mentioned that there are different kind of electronic phases exist in this material, which has different properties. So to understand the structure of these properties and the electronic properties, it is crucial to understand the electronic phases. And with the microscopy, we can do all these study. And I'll in fact also in the next slide also. Dr. Pranay has mentioned that on this slide only. Dr. Pranay has mentioned that this strain at this atomic scale plays a crucial role to change its structure, and thus its electronic structure, and thus it can also produce a new electronic properties. So therefore, understanding this nanoscale or atomic scale strain is very crucial, and transmission electron microscopy can give you this understanding. So now we can see that how much strain is coming between 2-3 atoms on the surrounding, how much strain is taking place if we are on the edge or if we are on the center of this material. So that could be understand. And for this material, having to have the understanding of strain is very important to see that how this strain is basically changing the phases of the material. And it's also very important to see that how these substrate is affecting this strain, and these how these strain effect is driving the new phase formation. And finally, the electronic structure. Obviously, all these properties comes from the electronic structure of these Borophene. So it is crucial to understand that how these electronic bands are changing at the atomic scale, how the multi-layers effect is like changing the structure or its properties, how the electronic states are changing when we are introducing more strain, how these defects are changing its electronic structure. So this all information is very important, and therefore these all key challenges are poses a great challenges in front of us before going for a practical application. So a microscopy can give all this information which can be leveraged for finding its ups or upscaling its production at a high scale. Next slide. Yeah. So here I basically summarize our plan that electron microscopy, the area that I'm working on, can give you all these answer on a single platform. For example, if you want to find that how much phases are existing of this material, there are techniques, for example, HRTM, high resolution transmission electron microscopy. So by image, you can itself see that how much different structure and phases are growing. Now, if you want to see that how the defects are forming, so these imaging techniques can give you a very direct evidence that what kind of defect is forming. If you want to see that how this growth is forming by this diffraction based study, you can see that how these substrate is modifying the growth direction of this material. Microscopy also gives you the answer that how the atomic scale strain is taking place. And of course, there are the spectroscopy method exists in transmission electron microscopy, which can give you the information that how the electronic changes are happening at atomic scale. So this is a one-stop solution to understand all these key challenges. And I just saw from this slide that how these all key challenges can be addressed. Next slide. So here I'm just very briefly showing some of our results related to Borophene. So we have, as Dr. Pranay mentioned, that the beta 123 and chi are two different phases, which very prominent phases, which have been very potential for these applications. And we have been successfully synthesized and imaged those. The uniqueness in this structure is that if you see this image number C, that it has some rich structure, and this rich structure has a higher electronic density, which are very mobile, and these are very responsible for these very anisotropic property of the Borophene. So we have in atomic scale, at the atomic scale, we can see those structure, we can see those two different phases. And of course, from the spectroscopy, which is electron energy loss spectroscopy here, we can see that we can verify that this is the pure phase, because every element has its own characteristic signal, which gives you the idea that what is its coordination number, what is its structure. Therefore, with the spectroscopy, we have verified that this is a pure Borophene phase. Next. Yeah. So Dr. Pranay mentioned that this material has a numerous number of allotrope and phases, and I can proudly say that we are some of the pioneer in this area. And there are different phases which have not been explored yet, and we have imaged, or I would say synthesis, some phases which is still not known to the scientific community. We are working on the experiments and trying to find that its application, and some of the application that we found that very important associated to these structures. So yeah, that is one thing. Second, it shows the very versatility as compared to the graphene. For example, these ABC images shows its nano ribbon kind of structure, so it's similar to the graphene. And recently, for the very first time, we have grown up the boron phene nanotube. Now, these tubes are very transparent and they are very flexible. So we feel that they have the potential that they can even replace this graphene nanotube. So with this, I would like to emphasize that we have discovered something, a very new phases, which is still not known to the scientific community, and they have very promising and potential application in different area. And we are looking forward, to gain this understanding and finding use these phases for some real world application, which Dr. Amitava will highlight after this. So Dr. Amitava, you can take over from here.
Thanks, Dr. Pranay and Dr. Negi. So let me summarize a little bit. So till now, actually, we have seen that we have listened that the synthesis of the material, then that atomic characteristic in the atomic level. So now we'll see that how the atomic structure looks like in the Borophene. by using various computation materials modeling tools. So this is just an introductory slide on this materials modeling. So materials modeling is a now well-known technique. So now people are using this materials modeling in various applications, like like this ASCII. There actually you can check that health of the nuclear missile without setting them off. Like in the Earth simulator, you can simulate that weather condition, and also we can check that material conditions or the material properties at the high temperature and high pressure region, like in the Earth mantle or Earth core. And if you want to evolve a new material, if you want to check a new material phase diagram, then also you can do from the materials modeling. So with this, let me start with this boron. So Dr. Pranay, the next. So the boron is actually a Z-1 neighbor of carbon in the periodic table. Boron is more or less similar to carbon atoms in the electronic properties. Now you can see that position between this metallic beryllium, the position of the boron, so which is in between this metallic beryllium and the non-metallic carbon. So this boron has only 3 valence electron. As you can see, this electronic structure, if you remember our class 10, that electronic structure actually helium, then 2s2 and 2p1. So this single 2p1 electron, that would favor this metallicity. But its orbital radius, which is very close to the 2s state. Now that is actually making it sufficiently localized to allow for the appearance of the non-metallicity. So now you can see that you have two different characteristics. One is that metallic characteristics as well as the non-metallic characteristics in the same material that you can tune. Now, such a unique electronic structure of this boron that enables the formation of a highly diverse bonding in the bulk phases. Okay, and this actually ranging from strongly covalent two-center bonds to metallic like multi-center bonds. Now, this multi-center bonds actually responsible of forming the polyhedron. Okay. Now, see, now both the theoretical as well as these experimental studies that have shown that small boron cluster, like in the figure, you can see this 1D planar structure is forming at the ground state. Now, if you see that you have the some structure that is, at that top corner, which is similar to graphene analog, but having a boron atom in the center of a hexagonal hole. Okay, so that means these 2D boron layers that are made of, you can see there is a triangular grid with a pattern of hollow hexagonal, the hexagonal hole you have. Okay, so now that is actually make it different, and create a difference in between your graphene structure as well as the Borophene structure. So, and this hexagonal hole pattern is actually highly variable in distribution as well as the concentration. Now, this is actually setting apart numerous lattices within a narrow range of energies that actually will give you different types of polymorphs in the Borophene. If you remember that Dr. Negi as well as Dr. Pranay said several times that Borophene could have the different polymorph. So this is the reason why the Borophene should have different polymorphs. Okay, now next, Dr. Pranay. Okay, so now it is no. So just go back to the slide, previous one. Yeah. Okay. So now if you see this band structure that is actually in the first billion zone. So interestingly, you can see this along the gamma to X direction, there is an energy band cross, the Fermi level. So that actually indicating that metallic properties of the Borophene. But however, if you see this gamma to Y direction, then you can see there is a direct band gap about around, let's say 2 eV. This is actually a band structure of a particular phase of Borophene. Okay. Now, as a result, that Borophene monomer is highly anisotropic. Okay, that we have already discussed, as Dr. Negi as Dr. Pranay said several times, that Borophene could show the anisotropic properties. So this is the reason of the anisotropy. Now that has a great impact on its optical as well as the carrier transport properties. Okay, now if you're talking about the electronic structure as well as the electronic materials, the carrier transport is an important features. Now, if you examine the density of state of the Borophene graphene, then this Borophene is the blue line and your graphene is the red line. So you can see that that there is a relatively large density of state near the Fermi, which is at 0, in case of Borophene monolayer, and indicating that very high intrinsic carrier density. Okay. Now let me bring this supercapacitor topic that has been discussed by Dr. Pranay, and he said that Borophene could be an excellent material in the supercapacitor, but why it should be? Now, if you see this supercapacitor mostly based on your electric double layer mechanism, that is mostly people are using this porous carbons or graphene as a electrode. Now the specific capacitance of this graphene that has been measured nearly in the range of 130 farad per gram in case of aqueous electrolyte, and if you use some ionic liquid, it will be kind of 90 farad per gram. So now this, however, this the graphene also could have very long cycle life, but the total capacitance of graphene is limited by its quantum capacitance, and that is due to its low density of states near the Fermi level that you can see in the figure. Okay. Now to address this issue, these researchers actually tried to done the doping the graphene with the heteroatoms such as nitrogen, and to increase the dose at the Fermi level. But if you do like this, this doping actually graphene fails to be very much effective, of course, but causing immense damage to the crystalline structure, to its honeycomb-like lattice for a long run. Now here Borophene that comes into the picture to leverage this 2D boron sheets metallicity and the lightweight of boron. And in fact, it has been noticed that some boron sheet could exhibit the specific capacitance on the order 400 farad per gram. So almost about 4 times that of the graphene. And most importantly, we can design the boron sheet only by changing the number of position of hexagonal hole and without adding any heteroatoms. Okay, that is one advantage, that we are not adding any heteroatoms. Okay. Now, so now if you talk, so go to the next one. So actually, in the previous slide, we have seen that based on the arrangement of these hexagonal holes, we can have different polymorphs of the Borophene. Now here actually I am showing you only 2 polymorphs, that is the beta 12 and chi 3, and both have the different arrangement of the hole structure. So now in addition to that, as I said, there's vacancy. We can consider the vacancy as a defect. Okay. Now if you say that you have this mono vacancy, now for example you want to use this Borophene as a electrode materials in the battery. Okay. Now one of the suitable position to fix or to seed this alkali metal ion like lithium, sodium, that could be on the your vacant side. Okay, that is in the middle of the hexagonal hole. Now if you do like this and if you stack this Borophene layer, you could make a similar type of anode materials, for example anode electrode materials like we have in the graphene. And as I said that in the previous slide, that Borophene could have a greater electronic properties as compared to graphene, so that could enhance your charge density. Okay. Now next, if you remember that Dr. Negi has shown that we have synthesized that boron nanotube. Now, as I said that there could be a different polymorphs of Borophene. Okay. Now here actually so we have studied that what kind of phases can form what types of nanotubes. If you remember our graphene analogy, so here actually in the graphene we have found that we could have zigzag, armchair, okay, depending on this rolling of your seat. Now here if you remember again that here seat means we have different types of seats correspond to different phase. Now that could give you different types of properties in your nanotube. So that is what actually we are doing. Now, in addition to that, in the previous slide, actually, Dr. Negi has shown that, and also Dr. Pranay mentioned that we could have some interface in between 2 phases. Now, here, if you see this figure C very carefully, if you follow that arrow here, so one side of the arrow is beta 12, another side is chi 3. So during this optimization process, you can see that how that structure at the interface rearranged. And if you see in the next structure, if you see follow the arrow, you can see in the previous one, you have little bit distortion around the interface, but in the next one, you can see that well arranged a new phase develop, okay, at the interface. Now, again, this could give you a different electronic properties. So that actually we are studying. So this is all about a little bit about the different phases and how it can give you the different types of electronic properties. Now, this is just a summary, just a brief overview that what actually this theory will participate, how theory will participate with these experiments, and how we can exchange the information back and forth. Okay. So now you can see this synthesis method that we have talked about, that we'll use various sonochemical method that involve the solvent. Now, the once you have the solvent, then you have to match the solvation energy with your material. Now here actually computationally, we can easily try different solvent and their solvation energy by using different types of computational tools like molecular dynamics or advanced molecular dynamics, those kind of things. Now, once we have this, information, we can also share this information to the experimentalist that you can use this kind of solvent, you can have this kind of charge density. And now in the characterization field, once you have this, electronic structure, then we can also calculate the optical properties, electronic properties of the material directly from the atomic structure. Now that properties will be compared of the experimental obtained properties. Okay. Now at the end, the application we are focusing right now, that is lightweight electronics in terms of EM modulus, area mobility, as well as the energy storage devices. Next. So now let me give you that brief overview that actually that world the people that actually working on the Borophene or focusing on the Borophene. So as you can see, this there's the recent news update, the press release from the MIT. So they are saying that the Borophene has a potential application. Now the world market is already on the rise. As you can see that MIT recognized Borophene as a wonder material beyond graphene, and they suggested that as a promising material in various applications like sensor, batteries, as well as the catalytic chemistry. Now another news that came from the Sunum University, Turkey. So that so they actually have started manufacturing of Borophene, and now just let me comment, only very few countries in the world actually manufacturing Borophene, and it's already pointed out by them. Now additionally, they have claimed that adding 3% of Borophene into a standard graphite based system that already we have, that could enhance the specific capacity of 20 to 30%. Now if you add more like 10% in supercapacitor, that we can increase that capacity up to 75%. That's a huge increase. Now not only that, that one of the big giant in battery industry, the Tesla, also on the gain. So in a recent interview, this Elon Musk said that Borophene will be a potential material for the electric vehicle. Now, although it is not clear whether they will use or maybe they're using, but as per our speculation that Borophene with supercapacitor, they may use in the SpaceX to fulfill the demand of the initial high power in the electronic circuit board during takeoff. Not only that, they are also exploring different battery chemistry such as lithium sulfur chemistry. This chemistry is little bit well known, but the one bottleneck that is also well known, that is the shuttling effect. Now the Borophene actually here can act as an anchor material to suppress this shuttling effect. That now it came to know that the China has recently that used this boron-based polymorph as a fuel for hypersonic missile. So there are plenty of application of Borophene that we have notified in terms of the battery. Now let's look into the catalyst. So as we all know that hydrogen economy, hydrogen energy, all these things. Okay, now the one of the bottleneck in the hydrogen economy or the hydrogen energy, the transport of hydrogen. That whether we want to transport in a gaseous form, that is very expensive, or liquefy, again you have to put energy, or in the gaseous form, liquid or solidify. Now, if you remember this ammonia, it has that formula NH3. So that means you have that 3 hydrogen already in the ammonia. So it can use as an energy vector. Now the synthesis of the ammonia till now is the Haber-Bosch process, that is we already know, but it is a very high temperature, as well as you can create a large carbon footprint. Now to bypass this, we can use the electrochemical method to synthesize same ammonia, but in the electrochemical method you need the electrocatalyst. Now this electrocatalyst, here actually you can use the different phases of Borophene. Like here actually we have already screened a particular phase of Borophene for the ammonia synthesis process. Next. Okay, so now the another application in the energy device like the hydrogen storage. Here actually also you can use that Borophene, since hydrogen atoms also actually stick easily to Borophene single layer structure event, and then this adsorption property and combined with the huge surface area of atomic layers, and also if you remember the lightweight of the Borophene, that makes the Borophene as a promising material for the hydrogen storage. Again, you can see that theoretically it has been predicted that it can store about 15% of its weight of in hydrogen. That is a significantly outperforming materials for the hydrogen storage community. Next. So now that this steel generation fighter, they are actually also you can use the Borophene. And now there are various techniques to suppress this radiation signature, the high radiation signature. People are using Borophene, and it's actually already nurtured by the outside people. Like it's actually working in this US university and the Rice University in the US. They have already started work on the Borophene with the particular phase. That is, we don't know that which kind of phase. But if you remember that we have also synthesized, also we have explored this material to use to seal that radiation. So next. So this that you can see that so there are plenty of application of Borophene that we have notified here, few on which actually we are working now. So Borophenes, it has a wide range of applications driven by its complex electronic structure, which actually makes the material as a next generation wonder material. So with this, we are concluding our TED talk here, and we will be happy to address if you have any further questions.
So thank you, Dr. Banerjee, for explaining things very coherently. And I would also like to thank Dr. Pranay for introducing us to the Borophene and Dr. Negi for explaining the key challenges. Now, I would like to ask I would like to open the session for questions. So if you have any questions, kindly type in the Q&A section, or you can also raise your hand. So any questions, please?
Already the question is there in the,
Right.
I think, question answer session. There are 2 questions.
Right. So we have 2 questions. So, so can you please answer the 2 questions we have?
Let me check the question where it's written.
It is in the question and answer session. I think in the below.
Let's copy the questions to chat.
Okay, yes. Dr. Pran explained the Borophene is grown on the metallic substrate. Could you please shed more light on the stability without the substrate? Can we get Borophene without the substrate? Okay, indeed we can get this Borophene without the substrate, and this is what I have done. This is what I have done over my PhD, and I overcome this hypothesis that it can be made in a freestanding sheet. Otherwise, its application cannot be imagined in this batteries and supercapacitor. About the deposition of Borophene on the metallic substrate, so that's basically a myth which we have busted. So the myth was that the substrate atoms is basically governing the growth of the Borophene, and that governance is basically determining the phase of the Borophene, which in real life is not possible. So this is what my hypothesis said, and this is what I have done an extra, or what the already existing theory was there in the scientific society till 2019. So yes, indeed you can make this Borophene as a freestanding, and this is what we have done. The next question comes to the reactivity. Just a minute, I missed the question.
There is one question by Ashutosh Jaiswal. I think that is you answered. I think, no? Is Borophene is a
the reactivity of Borophene? It has tendency to form the bond with substrate or other material. Could you please explain this? Yes, definitely. So indeed, Borophene is a reactive material. We cannot, simply bypass this, but it depends on what kind of reactivity it has. Okay, so now there's 2 kind of hypotheses in the scientific society. One is Borophene oxide, and one is adsorbed Borophene. So whatever the oxygen molecules it gets adsorbed on the surface, we call this an adsorbed Borophene. It's not oxide. Oxide means that you are infusing the oxygen atom in the lattice. That is not possible at room temperature. You need energy for that. So basically, although it's have that kind of reactivity, but that can be evaded providing some ambience or it can be evaluated providing some external energy. So in a lot of cases, what I came to through this scientific work, that people are ending up with some kind of dangling bonds, which is basically attached with some kind of atoms. So that can be removed with providing some kind of temperature, some kind of reduction technique. So yes, at last you can end up with Borophene, but yes, the tendency with formation of other element is there, but that can be avoided providing some kind of ambience. It's whether it's a vacuum, whether it's argon, whether it's nitrogen atmosphere, that can be avoided. What's the next question?
Total, there are 3 questions.
How could Borophene made in larger scale? Yes, since I talked in my slide that and as an analogy to graphene oxide, I've shown how reduced Borophene oxide can be made. So I not only through this sonochemical, I have tried to give the scientific society a new way to make this Borophene at large scale through chemical synthesis. So that's basically an ultra large scale synthesis of Borophene, and that's what we are doing in the lab. So that is a one-step solution what we have provided, and that the reaction is very unique till date. Where there's no reaction, exists in the scientific society. No other 2D material has been made through that kind of reaction. So we try to understand the mechanism of intercalation, exfoliation, and termination of the reaction, and based on each single step we segregated out which material is the best, which chemical is the best, and we end up with a one-shot solution of synthesis of Borophene oxide through boron. So role of Borophene in antenna. Yeah, exactly. When we are talking about this kind of 2D material, so terahertz application is always possible, but no one has explored. So if you are going with that, the hypothesis that if Borophene has been deposited in some kind of substrate, that's obviously been used as a terahertz material application. So that's a next generation material, and eventually people are working on Borophene based antennas, and that's again the, one part of the stealth technology which we have not presented here due to time constraint. But indeed, there are some countries, there are some peoples who are already working in this kind of thing where they have deposited Borophene, and to even mitigate, to enhance the property, they have hybridized the material with graphene. So what they have done, they have basically made a monoday of Borophene and graphene, and with the hybridization, they went one step ahead of making antennas. So yes, these things are already in their market, but it is at the research level. Can Borophene may be used in making nanodots? Indeed, Borophene can be used in making nanodots. Even Borophene dots are present. Even fullerene. If you talk about fullerene, like of carbon, Borophene buckyball structure is possible because it's the icosahedral structure. So that's the one phase we need to explore, and that we need to optimize the synthesis conditions. So it's all depend on what kind of application we are looking for, and how we are taking up the steps for making this kind of material. So yes, it has a lot of potential, I can say, and at this stage we have not involved our mind, or we didn't went to making this to a nanodot, but it can be made. It can be made. There's a possibility, there's a chances. You need to work on the kind of synthesis, and indeed it's possible to make nanodots. Can Borophene be used in sensing application? Definitely, we are also using in sensing application. So the Borophene, due to its high thermal stability and Young's modulus, people nowadays are using Borophene with sensor, because the BN bonding is the most sensitive bonding and most strongest bonding. So for nitrous gases sensing, even Borophene is the one shot of material which any one is looking for in the sensing domain. The next question is, can it be biologically synthesized? It's really difficult. Look, for thermostic application, we are working with University of Buffalo. So let me clarify in this way that at present we are working with Tata Steel, and with different universities like University of Buffalo, and Drexel is on top, and Newcastle University, where they all are involved in different kind of application of Borophene. So the Buffalo team is basically working thermostic application of Borophene with us, and optical electronics application. And it's a promising material because B10 at low Z value material, you can directly give the energy, and the photothermal effect is quite promising. So these are basically at research level. I cannot comment more than that, but yes, it is possible. But since the question is very specific about biologically synthesized, it's too early to comment on this. Can Borophene based material be used in high speed saver board to mitigate heat? Can Borophene be a great thermal management material? Look, as far as our knowledge, Borophene we are using for radar application, radar absorption. So this same material can be used for hypersonic missile. The same material can be used for frigates, sonars, and different warfares, because radar absorption can evade the signature of the system. This is the first. Now coming to your question, high speed severe board to mitigate heat. Indeed, this material has this application, and NASA is presently using this kind of material in MLI, multi-layer blanket, which is being used in space application. In the space, when you have a different kind of atmosphere and you have this meteors being striking to your material, to your system, or to your spacecraft, and at the same time there is charge accumulation, this kind of material is being thought of to use and replace the conventional 3D material, because not only it will enhance the property, it will also reduce the weight. So I have not used, but they are a scientific society. There are some groups which are using this for thermal blanket, multi-layer blankets. So yes, people are working on this. What happened when the Borophene structure breaks during charging? It's look, it's really difficult to say what happens when the structure breaks during charging. But one of the benefit of this is that when you are talking about superconducting or the charging or the supercapacitor, this kind of thing in a battery, you don't need electronic mobility. The more the dirty your material, the more good is the ionic conductivity. So even it breaks, although it's really difficult to break Borophene because it has the highest Young modulus. Okay, and we have shown this comparing to all the 2D materials. So yes, this is a next level question which we can only answer after having a clear details, clear study. But till 10,000 cycle, we have studied this material, and there's no change in any kind of signature what we are opting from charging, discharging. Till 10,000 there is no problem with the material. I don't know till what charging step the question has been asked, but yes, till 10,000 is quite stable. Hello, I want to know about the band gap of Borophene. Also, why it is direct band gap? Can Borophene also have different band gaps? Yes. Now, considering the band gap Borophene, it has a zero band gap. Okay, but the zero band gap relates to one particular phase of Borophene, that is the chi3. Coming to why there's a direct band gap, because there's a Dirac cone being formed in the chi3 structure. Coming to, can Borophene alone have different band gap? Yes, it can have, depending upon the different polymorphs of Borophene. Indeed, till 2.7 electron volt people have reported. So it all depends on the polymorphs of Borophene and the way you are synthesizing any Borophene sheets, because at last, if you're talking about a pristine Borophene, it should not have any kind of band gap. But when there's a protrusion, when the phase is coming from is changing from chi3 to the beta 1 to when there's a metastable stage, yes, you're opening with the band gap. Does the behavior of Borophene is different from carbon composites such that behavior in height? Yes, Borophene has a completely different signature, different property. You cannot compare Borophene with carbon at high temperature, because it's very stable. Till 2400 degrees Celsius, we have checked with our industry partner MEC, and it's quite stable. Is there any reference which explains the suppression of subtle effect and use Borophene as an anchoring material? I guess theoretically things has been done, but at present for anchoring material in experiment there's no such evidence, but theoretically there are a lot of evidence, because experimentally it's very difficult to talk about the anchoring side, because when you have a ridge, you have more of atoms, so more of atoms have more of electrons, so that's basically a thumb rule that it will give you the more anchoring side. So but experimentally it's really difficult to show, but yes, theoretically there are a lot of reports available in the scientific domain. Does the behavior Borophene is same as carbon?
Right, just one comment here. This lithium sulfur, I think we are talking about the settling effect in lithium sulfur chemistry. So there is, I think there is Northwestern University, they have done some preliminary work, okay, but I'm not sure about that, the other things, but they have done some preliminary work.
Okay, thank you, Dr. Amida. Thank you for pointing out this work. And the last question from Dr. Jitan: does the behavior of Borophene is same as carbon compounds such that behavior is high temperature and fatigue? So it's difficult to say because carbon do break at even not at very high temperature, but Borophene is quite stable at 2400 degrees Celsius. So things depends when you go to the application, but yes, it's going to be more enhanced when you are using Borophene rather than any carbon composite or graphene or any carbon hybridized material. Yeah, if there's any more question, do let me know so that I can talk about it. In case I have missed anything, please let me know.
You have
sir, there is a
completed
question.
the question and answer session
Yes,
that you have already completed, no?
okay.
Dr. Pranay, I think in a question and answer section, we have still some questions.
Yeah.
Yeah. Is Borophene used as steel coating? How it works? Okay. So yes, Dr. Jaishwal, this is like a trade secret between me and MEC Jodhpur. So at this stage, I cannot reveal this, but yes, we have worked on Borophene for steel technology. I am skeptical to talk about this at this stage, but yeah, we'll become like answering the things very soon. Really sorry to say this, but since these things are between two industry and academia partner, I cannot reveal this. Now, if I can go to the next question, can Borophene be coated on the radiator fan to mitigate heat? Of course it can be. Of course it can be. Now, the only thing is that we need to start doing this kind of application because it is a promising material and other 2D material has been investigated in that direction. So yes, Borophene has that potential to be applied on the radiator fan to mitigate heat. Can Borophene be used in sensitive application? Of course, it's being used, and it's like the one shot of material for nitrous gases sensing because the BN bond is really very strong and is very sensitive. So yes, Borophene is the best material for nitrogen sensing. Is there any reference which explains the separation of subtle effect and use it as an anchoring material? I think Dr. Amitava has answered this question. Yes, any more questions? I'd be happy to answer.
I think many questions were asked by.
Yeah, so in short, I'll give you the last. I would like to conclude from this remarks that we heard a lot of material during our current scientific research, but Borophene is something new and which is very thoughtful material because not only because it's been work has done by me or my team, because this is the only material which can change the future, especially when we talk about the supercapacitor and when you talk about energy materials. So this is the one sort of material which you don't require at 100% like to add to a particular application. Even you add 3%, you can see the changes is in 30%. When you add 10%, you can change the material specific capacitance by 75%. So even a smaller part of Borophene can change the game. And yes, Tesla is currently dominating the world market and is capturing the world with all technology available in Borophene.
One question is that how is India's situation now? India, as a India, see what is the situation for?
Yeah, okay. So in India, since we are the pioneer in this field and we are the first to do all these things, so we are currently working with Tata. So Tata is and Reliance both have approached us to make this material at ultra large scale, at industrial scale, but talks are going on. In addition, when you talk about Borophene synthesis in India, so none of the group in the world has this kind of facility in their lab, or they have this domain knowledge to synthesize Borophene. That's why even University of Buffalo, Drexel, and Newcastle is working with us, because we are the only one in the world to make this as a freestanding.
How can we go further?
We can definitely go further from lab to fab, depending upon the availability of boron, which India has recently got in Ghatsila. And so, yes, the source is a challenge, but when you have a source, you can, like, even it's very, economical if you consider converting graphene to graphene oxide. So even it's cheaper from that synthesis process. So the only concern is boron, which need really government interference, clearance. If that is done, it's very easy to synthesize the material and go to the application part.
I think we can work together, ELCINA, as well as our all people. Let us form a close group and let us work together how we can, in fact, more potential on a case study on if any case is there already. Let us form a close group. If the people are interested, they can send mail to either EFY, ELCINA, or professor. So we can form a group, and every month or two we can discuss, and let us send a proposal. What further we can do so that India is basically can do a much better job.
Yes. Even whatever the supercapacitor and battery companies are available in the market, if we can enhance their property even by just adding few gram of Borophene, that would serve the purpose of having this kind of material in real time application.
So I request all the attendees, if you are really want to work something, let's volunteer yourself also. And our professors are already there. They are the, let us work closely and how more and more this technology could be brought in India and used it in a proper manner. That's the basic idea.
Thank you, sir. I guess all the questions are answered, and thanks a lot, Dr. Pranay, for explaining everything so coherently, and Dr. Amitabh Banerjee and Dr. Negi for introducing us to this amazing material. So I think we all had a very good session, a wonderful session, and everyone has learned a lot. So ladies and gentlemen, we have come to the end of a wonderful session, and I hope that all of us leave enlightened by the thoughts and experiences shared by our eminent speakers. I would also like to thank all of you for coming us and joining us here today and taking out time from your very busy schedule. Now, I would request Mr. Raju Goelji to give a vote of thanks or to conclude the session.
Yeah, basically from ELCINA, I'm so
Okay,
thank
sorry,
you very much to all our three professors. Very delighted presentation and work. So first of all, I should thank Dr. Pranay Ranjan, the Assistant Professor, Department of Meteorology and Material Engineering, IIT Jodhpur, who talks about the hypothesis that freestanding borolene, and he is the first to synthesize the borophene, and his talk is really very wonderful. I also thank Dr. Devendra Singh Negi, the Assistant Professor from IIT Jodhpur, who basically talks the role of atom and how the entropic driven properties. And finally, Dr. Amitabh Banerjee, the Assistant Professor, IIT Jodhpur. He talks about the structure and molymorphism of borophene, and really given a lot of example by all these three people. And with this, I think India is more potential what Tesla is doing with the help of the three professors and the knowledge. We can have some kind of PUC for the electronics industry. And I thank all the attendees who has joined. Looks to be little more technical. Three people have worked a lot. So few people feel it's a little technical, but it's good. And we hope that ELCINA EFY and the IIT Jodhpur can work together. And like the last budget, government has declared for artificial diamond project. We can also request government for this project can also be funded. For that, we need the stakeholders. So I request all the participants, they can come as a group, join in our closed group, and we can prepare a proposal and submit to government. With this, and thank you very much for our knowledge partner EFY, putting a lot of effort, and I congratulate them for their hard work. Thank you very much.
Thank you, Dr. Raju. Thank you, Dr.
Thank
Saurabh.
you.
Thank you all. And thank you for giving the opportunity. I hope we'll meet soon and we'll do together something good for the scientific society. Thank you all.
Thank you, everyone. And as Dr. Dubey also said, to form a closed group for all the interested people. So I think we have a lot of requests from people who want to join this group. So I guess it was indeed a wonderful session and everyone enjoyed a lot. So thank you.
Thank you. And just do let me know what next need to be do for this forming the team, and how do we communicate with each other.
Right. Yeah, let us form a WhatsApp group or something like that. I think EFI can do it, and let us closely work together, make the proposal and sometime we can work together also. Right. Thank you very much.
Thank you, everyone. Thanks a lot.
Thanks
and have a great weekend.
Same to you. Thank you. Thank you all. Goodbye.
Thank you all for joining.